Hello and welcome to Chemistry with Dr. Clark. This is part 3 of a 3-part series on the solubility product constant. So in this series of videos, we talked about if you have a low solubility compound. So you have some sort of substance, it doesn't like to dissolve in water. So when you put it in water, it does break up a little, but it breaks up very, very little. So a little tiny bit of it will dissolve, but not very much. So in these problems, what we want to be able to do is calculate either the solubility or the value of the solubility product constant. Okay, so I have both defined here. Right, our solubility product constant is just an equilibrium constant for that solid substance attempting to dissolve in water. The solubility of the substance is the maximum amount that can be dissolved in water. Now, the solubility here is going to be low, extremely low, because these compounds really do not like to dissolve in water. So now to do this problem, you are going to have to write an equilibrium expression. You are going to have to be able to write the equilibrium itself. And both of those are covered in the first video of this series. So if you're not feeling super comfortable with writing the equilibrium that goes with a low solubility solid dissolving in water, or if you're not feeling totally comfortable with writing an expression for the solubility product constant, you might want to pause the video and go back and take a look at part number 1. In part number 2, we talked about problems that gave you the solubility and asked you to calculate the value of the KSP. If that's the kind of problem that you're attempting to solve, you might want to pause again and go back to part 2. Here in part 3, what we'd like to be able to do is I would like to be able to give you the KSP and ask you to calculate the solubility. Giving the solubility or giving the KSP, those two sets of problems are very, very close. The steps that you'll follow will be almost identical till you get almost to the very end. Okay, so it might be worth going back and taking a look at part 2 of the video series. Now, the easiest way to do this would be to take a look at some actual problems. So let's say the problem says, calculate the solubility of nickel 2 carbonate if its KSP value is, and I'd like to calculate the concentration of the cation in the saturated solution. All right, so the very first step in these problems, whether you're looking for solubility or whether you're looking for the KSP, is write the equilibrium. You need to write an equilibrium for this low solubility solid dissolving in water. So if we try that, I've got nickel 2 carbonate. It is a solid. And when I put it into water, it will dissociate. So the nickels and the carbonates will separate from each other. So I will get some nickels and I will get some carbonates. Now this is an equilibrium because as some of the solid nickel 2 carbonate falls apart, some of the ions that have separated will come back together. So you get a cycle. Some will fall apart, some will reform. Some will come apart, some will reform. So it is an equilibrium. Now, if you go back to part 1 of the video series, when you write this equilibrium, there's a couple of things that you have to include. These, when they break up, are aqueous because they are surrounded by water. You do need to balance the equation. So for this particular problem, you started off with 1 nickel and you still have 1 nickel, so that's balanced. You started off with 1 carbonate and you've ended with 1 carbonate, so that's balanced. Okay, in this particular reaction, it is a 1 to 1 to 1 reaction. Now, in a couple of the later examples, the balancing is not 1 to 1 to 1, but I thought we'd start with an easy one at the beginning. The other thing that you really need is the charges on the ions. So if you look up carbonate on your polyatomic ions table, you will see that it has a charge of 2 minus. Now the nickel is a little bit trickier because it is a transition metal. Because it's a transition metal, it potentially has more than one possible charge. You can have nickel 1 plus, nickel 2 plus, or nickel 3 plus. The easiest way to figure it out is by looking at the anion. In an ionic compound, the total number of positives and the total number of negatives have got to match. So if you've only got one carbonate and one nickel, then the charges have to match and balance out. So if the carbonate is a 2 minus, this nickel has got to be a 2 plus. Okay, so this is your equilibrium. Your low solubility solid splitting up to give you ions. Now, I also need to talk about my KSP. So if I'm going to write my KSP, let's put that maybe down here a little bit. KSP is just a very specific type of equilibrium constant. And all equilibrium expressions put the products in the numerator and the reactants in the denominator. So your first product is a nickel 2 plus. We put square brackets around it to show that it's a concentration. And whatever number was used to balance it becomes your power. So it'll be power of 1. The second product is a carbonate, so CO3 2 minus. We put square brackets around it to show concentration. And again, a 1 was used to balance the equation, so we have power of 1. Now, normally at this point, I would draw a line and I would talk about my denominator. My denominator would be my reactant. But as I've already talked about in this series of videos, if you have a solid, solids and liquids are not written as part of your equilibrium expression. They're just left out. So really, even though the nickel carbonate solid should be down here in the denominator, because it is a solid, I'm allowed to leave it out. Okay? And that's explained in a bit more detail in the part 1 of the video series. Now, the easiest way to do this type of problem is to build a nice table. Okay? So if we build our table, each of the products get a column. So if you've got 2 products, you get 2 columns. And in this table, you do need to have 3 rows. Okay, so we'll just extend a little bit. There we go. So you've got 1 column for the first product, you've got a second column for the second product, and you've got 3 rows. And the reason why we call this an ICE table, ICE, is because the first row talks about initial. This is the initial concentration of the products. Then we talk about the change in the concentrations. And then we talk about what happens at equilibrium. And equilibrium is a bit of a long word, so we do abbreviate it as EQLBM. Okay, so initially, you've put your nickel carbonate in water. You have given it exactly 0 seconds to break up. So if you've given something 0 seconds to split up, how much is split up? None. So for this problem here, you would have none of this and none of this because you have not given it enough time to actually dissociate, to dissolve, right? To break up. Now let's talk about the change. The change happens because you now give this thing time to reach equilibrium. So you are going to gain some of the nickel 2 plus and you are going to gain some of the carbonate solid. How much you're going to gain? I don't know. So you have to give it a variable, and the variable that we like to use is S. Now for this problem here, the amount of each one you get is dependent upon the balancing. So for this particular problem, you had 1 nickel for every 1 carbonate. So the number, the change, should be the same for both. But let's say for every 1 of these, you got 2 of these, right? So you'd get twice as much of your carbonate. So whatever numbers you use to balance the equation, they do go in front of your changes. Now for this particular one, because it is a bit of an easy example, and it's 1-to-1, it doesn't really make a whole lot of difference whether you put it in or not. But in later examples, when it's not 1-to-1, it becomes very important to put these numbers in front of your S. Now, what do you have at equilibrium? Well, it's what you started with, plus how much you changed, gives you the equilibrium. So if I started at 0 and I added S, that's like saying 0 plus 1S. If you add 0 to anything, it stays the same, so it's 1S. And if you think in terms of math, if you had like 1x, do you really need to write the 1? Not really. So 0 plus 1s is S, 0 plus 1s is S. Now, if you've already taken a look at part 2 of this 3-part series, what you'll find is that everything that I've done so far has been exactly the same as in part 2 of the video, right? These problems are very, very stepwise, right? They always follow the exact same steps every single time. Step 1, write out your equilibrium. Step 2, write out your equilibrium expression. Step 3, build yourself an ice table. Okay, the first few steps are always the same, which is why these KSP problems are so nice. Because once you learn how to do one, you really do know how to do all of them. Now, what I'm going to do is I'm going to substitute these values into my equation. Okay, so if we talk about our KSP, there is my KSP. How much nickel 2 plus do you actually have? Well, I have S of it, right? How much nickel 2 plus? I have S. Now, this is an equilibrium expression. Because this is an equilibrium expression, you have to use the equilibrium concentrations, right? They go together. Equilibrium concentrations go into the equilibrium expression. So I don't know exactly how much nickel 2 plus I have, but I've decided to give it the symbol S. And it is to the power of 1. How much carbonate do you have? Well, carbonate, I have S as well. So S to the power of 1. Now this does become a bit of a math problem, right? If you had x to the power of 1 times x to the power of 1, you'd end up with x to the power of 2. I'm using s's instead of x's. So my KSP would be s squared. And again, if you go back to the second part of this video series, when we were talking about I'm going to give you solubility and ask for KSP, right, the opposite problem, every step so far is identical, right? Write my equilibrium, write my expression, write my ice table, and then substitute these values into the expression. It's only here at the very end do the two sets of problems differ. In the last video set, I would have given you the S and asked for the K. For this one, we've just reversed it. I've given you the K, and I would like to know solubility, right? Calculate the solubility. So if I put in my value of K, that's 1.4 times 10 to the power of minus 7 equals S squared. If you want the S by itself, you're going to have to take the square root of both sides. So we'll just square root both. All right, we'll move it up just a little tiny bit. Square root of S squared is S. And if we pull out our calculator, 1.4 exponent 7 negative. In my calculator, in order to put in scientific notation, I have to use the EXP button. And then I just take the square root of it. So second function square root. So that gives me an answer of 3.74 times 10 to the minus 4. Now, the S that we use here, the reason why we use an S and we don't use an X is because the S refers to solubility, right? How much of this stuff dissolves? Well, it's right here. How much nickel did you get? I got S of it. How much carbonate did you get? I've got S of it. Your S is your solubility. It is the maximum amount of this solid that you can dissolve in water. Now, if it's a solubility, solubilities are always measured in moles per liter. So don't forget to throw that in at the end. So if you attempt to take some nickel 2 carbonate and dissolve it in water, how much are you going to dissolve? I will dissolve 3.74 times 10 to the minus 4 moles per liter. Now, if I turn that back into a decimal number, that's 0.000374 moles per liter. That's a ridiculously tiny amount, right? This is how many moles you could dissolve in 1 liter, right? That is extremely small, which is reasonable because these things dislike dissolving, right? They do not like to dissolve. They will only dissolve a small amount. Now, for these problems, sometimes that's all they'll ask, right? They'll give you the KSP, and they'll ask for the solubility. But often, they'll ask for like a part B. The part B would be more of a, so once you know the solubility, could you find the concentration of the cation, or perhaps the anion, or perhaps both? Now, the reason why this is such a nice little part B is because you've done all the work. How much of the cation do you have at equilibrium? Now remember, the cation is the positively charged ion, so the nickel 2 plus is the cation. How much do you have at equilibrium? I have S. Do you know the value of S? Why, yes, I do. So when it asks, what's the concentration of the cation in a saturated solution? What they're really saying is down here in this last line of the table, can you fill in the values for the S? So how much nickel 2 plus do you have? I have 0.000374 moles per liter. That is the concentration of the cation at equilibrium. Now, this particular problem only asks for cation, but if it did ask for the anion, all you'd have to do is put the number right here and tell me how much of the anion you have. Now, the problems don't always ask for that, but sometimes they do because it's such an easy part B. All right, now that we've run through kind of the procedure for this, let's try another one. Okay, so it says, please calculate the solubility of copper 2 hydroxide if its KSP value is this, and then calculate the concentration of the anion afterwards. Now these problems all follow the same steps. Write me an equilibrium, write me an equilibrium expression, make an ice table, and then move the values of S into the equilibrium expression. It's only at that very last step do you have to decide, do I have the S or do I have the KSP? Okay, so let's write our equilibrium. I have copper 2 hydroxide. These things always start as a solid. They always break up through equilibrium, right? Because they break up, come back together, break up, come back together to give me the ions. Now the two ions that are going to make up this, you've got coppers and you've got hydroxides. So coppers and hydroxides. When they break up, they are aqueous, so aqueous and aqueous. Now you have the balance. In this particular problem, I started off with 1 copper, and I still have 1 copper. But I did start off with 2 hydroxides, right? The bracket with the 2 tells me that there's 2 of them. So I'm going to have 2 hydroxides. Okay, now if we talk charges, the hydroxides are polyatomic ions. So if you go to your table of polyatomic ions, they are -1. The copper, though, is a transition metal. And like I said before, transition metals can have more than one charge. This could be copper 1 plus, 2 plus, or 3 plus. The easiest way to figure out what you've got is by looking at its partner. I have 2 hydroxides. Each hydroxide is a -1. So the first one's a -1, the second one is a -1. So I got a total of 2 minuses, which means I need a total of 2 positives. There's only 1 copper, so it would have to be a 2 positive. Okay, now I know that I'm going to be building a table here, my ice table, so I'm going to skip a bit of space and do my KSP down here. So KSP equals first product, copper 2 plus, put it in a square bracket to show that it's concentration. I did use a 1 to balance it, so let's put a power of 1 here. The second product is a hydroxide, minus. Put it in square brackets to show that it's a concentration. And for this one, in order to balance it, I had to have 2. So the power here is going to be 2. The denominator should be my reactant, but my reactant is a solid, so I get to leave it out. Okay, this is my equilibrium expression. All right, let's build ourselves a table. Each product gets a column. So I would have 2 products, 2 columns, and you have to have 3 rows. Initially, change, and equilibrium. Now, if we talk about our initial, just like the last time, you have put this stuff in water, and you have given it exactly 0 seconds to break up. So if it hasn't had a chance to break up, that means you've got zeros. Now, the change means that you actually did take some time and give it a chance to actually start splitting up. How much did it split up? I don't know, so we'll call it S. It is a plus because you are adding extra that has split up. And this is where your numbers come into play. For every one of these that breaks up, you get one copper, so I get one of those. But for every one of these that breaks up, I get two of these. I get twice as many. Now what you'll notice is that the numbers used to balance show up in two places. They show up in my table in the change section, but they also show up as my powers. Power of 1, power of 2, right? 1s, 2s. So when you balance this equation, those numbers end up in your table, but they also end up in your equilibrium expression, both places. Okay, that's really important not to lose them. Now again, like last time, if you have 0 plus 1s, that gives you s. If you have 0 plus 2s, that gives you 2s. And again, like the last time, I'm simply going to take the equilibrium numbers and put them into the equilibrium expression. Now, I was a little hesitant to call them numbers because they're not numbers, they're s's. But the idea is, whatever's in this row, you're going to dump into this equation. So how much copper 2 plus do you have? I have S. So that goes in for the copper. How much hydroxide do you have? I have 2S. So that goes in for the hydroxide. So my KSP is going to be the amount of copper 2 plus, that's an S to the power of 1, times the amount of hydroxide. That's a 2S squared, right? Now if I put the 1 back, this was 1S to the power of 1. This is 2S to the power of 2, okay? Now it does become a math problem. So if I work it out as a math problem, if you've got 1s to the power of 1, that doesn't change it, it's just an s. If you've got 2s squared though, that squared belongs to the 2 and to the s, both of them. So 2 squared would be 4, and s squared would be s squared. So my KSP is s times 4s squared. Think of it like x times 4x squared, right? X times 4x squared would give you 4x cubed. So s times 4s squared would give you 4s cubed. A little bit more complicated than example number 1, right? Once you start getting numbers other than ones when you balance, it gets a bit more complicated. Now, we're going to need a little bit more room. But before I do that, maybe I should pull down my value of K. In this problem, I'm either going to give you the K and ask for the S, or I could give you the S and ask for the K, right? That's the only two possibilities. In this particular problem, I have given you the value of K. So I've told you that the K is 1.6 times 10 to the minus 19, which equals 4s cubed. Okay, now we can move it up. Now for this problem here, you have to get the s by itself, which means you got to get rid of the 4 and you got to get rid of the 3. You're going to divide off the number multiplied first. Okay, that's the way the problems will work. So the first thing I have to do is get rid of the 4. So I'm going to take both sides and divide them by 4. Right, for this problem here, whatever number is in front of the s, you'll divide that off first, and you deal with the power second. Okay, so let's move it up a little bit more. So if I have 1.6 exponent 19 negative. Oops. 1.6 exponent 19 negative. Right? Make sure we type it into our calculator correctly. If I divide that by 4, I get 4 times 10 to the minus 20 equals s cubed. Now, the last time when you had an s squared, the opposite of squared was square root. The opposite of a cube is a cube root. So you have to do a cube root. Now, your calculator may actually have a button that says cube root, or if you've got a nice fancy calculator, it may have a button that'll allow you to do any root you want. Third root, fourth root, fifth root. My calculator does not. So I have to take an alternate way to do this. If you're taking the cube root of a number, 4 times 10 to the minus 20, that's the same as taking the power of 1/3, right? If you had the fourth root, it would be like the power of a quarter. If you had a fifth root, it would be power of 1/5. Okay, so I have to do this with my calculator because my calculator doesn't have a cube root button. Now, if you're taking the cube root of s cubed, that's just s. So all I need to be able to do now is take this number and take the cube root of it. So 4 to the power of 20 negative. Okay, so that's 4 times 10 to the minus 20. X to the y, and 1/3 is 0.333333. So my calculator tells me the answer is 3.4 times 10 to the minus 7 equals S. Now the S is your solubility. And if it's a solubility, you have to have units. So this would be moles per liter. So if you attempt to dissolve copper 2 hydroxide in water, you will be able to dissolve 3.4 times 10 to the 7 moles in every liter. That is a ridiculously tiny amount, right? Really, really small. Now, if the problem had only asked me for solubility, I'd be finished. But the problem did go on and say, oh, once you've calculated the solubility, I'd like you to do some extra work. So it does ask us to find the concentration of the anion. So here's my anion. Let's find the concentration. Now, I haven't left myself a whole lot of room here, so maybe what I should do is like just draw a little arrow down here, right? Maybe what I should have done was take this calculation and moved it to the side, so that way I had some empty space under my table. That way, when they asked me to do this, I'd have a place to do it. Now, if you want to know the amount of hydroxide, it's not just S, it's 2S, right? How much hydroxide do you have? How much of the anion? I have 2 times S. Because for every one of these you break up, you get twice as much hydroxide. So if the solubility is this, that's how much of the original copper 2 hydroxide can dissolve. You're going to get twice as many hydroxides, right? Twice as much. So for this problem here, I'm going to have 2 times, let's move it up a bit, 3.4 times 10 to the minus 7. And if we haul out our trusty calculator, 3.4 times 10 to the power of minus 7 times 2 gives me 6.8 times 10 to the minus 7 moles per liter. And that's going to be the amount of hydroxide. Because for every one of these, you get twice as many hydroxides. So if the solubility is 3.4 times 10 to the minus 7, the amount of hydroxide is going to be twice as much. Okay, now if I had planned the problem out a bit better, I would have left a bit more space under my table, so I could have done this right here under my table. Okay? All right, and I do have one extra one. Let's go through this one a little quicker. The main purpose of this one is so that afterwards you can restart the video to this point right here. Try the problem yourself because it is very important that you do these problems yourself. And then follow through and allow me to do my calculation. And then you can compare your answer to my answer, right? That is the main purpose of this last example, is just to give you a chance to try it yourself and see where you go right and where you go wrong. All right, so if we write out our equilibrium expression, nope, our equilibrium. We just want the equilibrium first. I've got Ca3PO4 twice. It is a solid. Some of it will break up through an equilibrium to give me calciums and phosphates. So I will get calciums and I will get phosphates. If you look at the numbers here, this thing has 3 calciums, so I'll need 3 calciums. It has 2 phosphates, right? This is my phosphate, and I've got 2 of them, so 2 phosphates. So 3 calciums to 3 calciums, 2 phosphates to 2 phosphates. It's balanced. I should call these both aqueous because they're both dissolved. And I need to do charges. Now for this one here, it's actually a little easier because phosphate's a polyatomic ion, so you just look it up, it's a 3-. The calcium, though, is in group number 2. If you have an element in group number 2, its charge is going to be 2+, right? This is not a transition element, so there's no wiggle room. There's no trying to decide what the charge is. You should be able to go to your periodic table and just look it up. Now, this here is a very messy balance, right? I've got a 3 and a 2. So in my table, I'm going to have a 3 and a 2. And my equilibrium expression, I'm going to have a power of 3 and a power of 2. Right? It's going to make the problem a bit more complex. But it's going to follow all the same steps. So as long as you do the same steps every single time, you should be good. So if we write out our KSP, my KSP is first product, calcium 2+, square brackets, to the power of 3. Second product is PO4, 3-, in square brackets. And because there's a 2 used to balance it, this is power of 2. Equilibrium, equilibrium expression. All right, let's build ourselves a nice table. 1 column per product and 3 rows. Initial, change, and equilibrium. Now, when I fill this one out, just like the last 2, initially, you've got 0 time. If you've got 0 time, then none of this and none of this has formed, right? There hasn't been enough time for them to split up. If you do give it time, you will gain both of them, right? Because over time, they will split up. And so you're going to gain an unknown number of these and an unknown number of those. They're both S's. Now, for every one of these you break up, you get 3 calciums. So I get 3 times the solubility. For every one of these that break up, I get 2 phosphates. So 2 times the solubility. 0 plus 3s is 3s. 0 plus 2s is 2s. And just like every other problem, I'm going to take the value for the calcium and substitute it in for the calcium. I'm going to take the value for the phosphate and substitute it in for the phosphate. So my KSP will equal, how much calcium do you have? I have 3s to the power of 3. How much phosphate do you have? I have 2s to the power of 2, right? 3s to the power of 3, they're both 3s. 2s to the power of 2, they're both 2s. Now the problem just becomes an exercise in can you make the math work? Right, so if we move this up a little bit, KSP would equal, remember, power of 3 belongs to the 3 and the s. Power of 2 belongs to the 2 and the s. So 3 to the power of 3 is 27. S to the power of 3 is s cubed. 2 to the power of 2 is 4. S squared is s squared. So my KSP equals 27 times 4. Well, pull out your calculator for that one. 27 times 4, 108. And an s cubed times an s squared is an s to the 5th. And once again, it doesn't matter if you were looking for K or looking for S. The problem is exactly the same until you get to this point. It's only here do you substitute in the one that you're given and find the other one. Now, I know that the math on this one is a little bit more messy, but you're going to do it exactly the same way, right? I'm going to get rid of that 108 first, and then I'm going to get rid of that power of 5. So if we look up here above, the value of KSP was 1.3 times 10 to the minus 32. That equals 108s to the power of 5. Okay, let's move it up. You always move the number that's multiplied in front first. So I'm going to divide off the 108, divide off the 108. Okay, so 1.3 to the power of 32 negative, divided by 108. So if I do that, that gives me 1.2 times 10 to the minus 34 equals s to the power of 5. And if you've got an s to the power of 5, the only way to get rid of it is to take the 5th root. So 5th root. Again, if you have a nice calculator, it may be able to take the 5th root for you. My calculator's not that nice. So for my calculator, I will have to do the 1.2 times 10 to the minus 34 to the power of 1/5, right? Fifth root is power of 1/5. S to the power of 5, and you take the fifth root, they cancel out, so that leaves an S. So with my calculator, I'm going to take this and raise it to the power of 0.2, right? 1/5 is 0.2. So my calculator gives me an answer of 1.6 times 10 to the minus 7 equals S. S is your solubility, which is what you're looking for. And because it is a solubility, this would be moles per liter. All right. The math here is not overly bad. It looks terrible, but it's not any different from the earlier problems. The main issue that you may have here is getting your calculator to do the problem the way you want it to. Okay, so you're going to have to practice with your calculator a bit. That's the reason why I say you should rerun the video, stop when I give you each of the problems, attempt the calculation yourself, and then go back and check and see how your answer worked out. Okay, now for this particular problem, I did say, once you find the solubility, could you please find the concentration of both the cation and the anion? Okay, so I want it both. Now again, I don't have a whole lot of room here, mainly because the pens make the calculations quite large. So what I'm going to do is just kind of slide these to the side. Okay, for you, if you're using like your pencil, you should be able to split them apart and give yourself lots of room. So if I want to know how much calcium 2+ I have, that's going to be 3S. If I want to know how much phosphate I have, that's going to be 2S. And all I need to do is take the value of S that I just found and put it in. So how much calcium do you have? I have 3 times 1.6 times 10 to the minus 7. Okay, so 3 times 1.6 times 10 to the power of minus 7. That is 4.8 times 10 to the minus 7 moles per liter. So this would be the amount of calcium 2+ that I have. How much phosphate do you have? 2S. So 2 times the value of S. The value of S was 1.6 times 10 to the minus 7. You multiply that by 2 in your calculator, gives you 3.2 times 10 to the minus 7. And it would be moles per liter concentration. Once you know the solubility, once you know how many of these break up, then it's easy to be able to tell how many of the anion you'll get and how many of the cation you'll get. And that is often the secondary question here. All right, so I wish you the best of luck in these calculations. And as always, thank you for joining me here at Chemistry with Dr. Clark.